Hello everyone, my name is Manya Agarwal and today I'm going to present on the topic of optical microscopy. So in simple terms, what does microscopy does? So microscopy is used to magnify the object so that you can um, see it more clearly. The minute details of the object, you can see it clearly through naked eyes. That is the purpose of doing microscopy. So here we are going to study about optical or light microscopy, in which light is used as the source of the light. And so in this image, you can see it is a very magnified image. Apparently, this is the image of a Arabidopsis thaliana leaf, and you can see the very sharp details can be seen in this image. So this is possible using microscopy. So the earlier image that we saw is a digital image, but on your screen is the optical microscope, a simple schematic showing showing the essential components of a microscope. So this is a very simplistic model. Nowadays, many sophisticated models, many sophisticated uh, microscopes have come up in which there are greater specifications and enhanced methods. The components are very much advanced and um, complicated, but in this image we are going to see the basic pieces that form an optical microscope. So let's start from the top, and at the top we have the eyepiece. So eyepiece is where you rest your eyes and you see the magnified image. Beneath it is the body tube. It is the place where the image from the objective is being formed. So this is an important so this tube length is important in knowing the magnification of the microscope. Next is the revolving nose piece along with the objectives. So there is a nose piece which you can revolve so that the different objectives come to see the object or the sample. So an objective is nothing but a lens which sees your sample. So beneath the objective is the stage where the sample is kept, and under it is a condenser. So what does a condenser do? Basically, it collimates the light. It pulls the light that is coming from the source. And at the bottom most we have the source, the lamp that is used. And there are some other small things, like he in this model you can see there is a two knobs. One is for the coarse adjustment and one is for the fine adjustment. So when you deal with the technicalities of a microscope, you need to understand how to bring the image to the focus, and in that these adjustment knobs are very useful. So this was a simple schematic of an optical microscope. Nowadays very sophisticated devices have come up, but essentially all microscopes are based on these components only. Now coming to the how we are seeing the magnified image, like what is happening, what is the how do we see a magnified image is explained using these ray paths. So we have these two lenses, that is the objective lens and the eyepiece, that and the final image is what we see is through the eyepiece. So these two lenses there is an interplay between these two lenses, and that gives our image. So let's see. So first of all, we have our object placed at a distance z, and this is represented by a small h. So our object is having a height small h. when the rays from the object falls on the objective lens, there is a refraction of light, and then they form an image at the intermediate plane. So this is the image formation, which you can see is a bit magnified, and this is a real and inverted image that is formed at the image plane. It is formed at a distance z prime from the FB. Now, this intermediate image is not the final one. Now the rays from this intermediate plane goes to the eyepiece, and after refraction, the light falls on our retina of the eye and we see the final magnified image. Now, the earlier one was the finite tube length microscope, but nowadays we have infinity corrected microscopes. So, what are infinity corrected microscopes? They are made to um, circumvent the problem of the tube length. So, that tube length plays an important role in the magnification, as you will see in a few minutes. So, this infinity connected microscopes helps to overcome that limitation of the finite tube length. And what is the difference? The difference is the use of this tube lens in between the objective and the eyepiece. So you can see a third lens, that is the tube lens, and its role is to produce parallel rays from the lens. So these parallel rays are able to produce magnified images which are able to produce magnified images despite of the length of the tube. So if you have a smaller tube length also, then also you will get a very magnified image because of this infinity corrected microscope. So let us see the mathematical treatment to obtain the magnification from our optical microscope. So before that, we will see some um, glossary. So the height of the object is represented by small h. The height of intermediate image is denoted by h prime. The focal length of objective is small f. The back focal length of objective is f prime. F is equals to f prime, and the object distance from objective is given by a small a, which is nothing but f plus z. The microscope tube length, or it is the intermediate plane distance from the objective, is given by small b, and it is equals to f prime plus z prime. So now the magnification of image at the objective, which is given by m subscript o, is equals to h prime over h. So magnification, we know it is the image height over the object height. So h prime over h. Now what is h prime? H prime is nothing but b into h over a. This we can arrive at using the lens formula. So then we will get h prime as b into h over a. Then MO becomes B by A. Simply by H prime over H, we get MO as B by A. And a small mathematical relationships will land you to this analogous formula for MO, which is F by Z, or Z prime over F prime. So over here you can see that Z or Z prime uh, appears in the formula of MO. So Z prime is the intermediate or the rear focal plane of the objective. So essentially the tube length. It is a measure of the tube length. So that is why we infinity corrected microscopes are used to um, get a better magnification from a finite tube length. And the magnification at eyepiece, which is given by m subscript e, is given by 25 over fe. The 25 comes from this 25 is because of the near viewpoint of our eye. So our eye cannot see a distance closer than 25 centimeter. We cannot resolve the images which are within 25 centimeter. At least this much distance is needed for a clear image to be observed. So this magnification at eyepiece is given by 25 over FE. FE is the focal length of the eyepiece, and the total magnification is given by MO into ME. A side note, the virtual or the visual image appears to the observer as if it were 25 centimeter away from the eye. Next is the fundamentals of image formation. So how is the image getting formed? So let's dive into this. So when the light from the source comes and interacts with our sample. So first we have the source, and from it we have the light. When the light passes through the sample, there is some light that goes directly through the sample and to the objective. That light is called the undeviated light. It is not interfering with the sample, it is directly going to the objective. Or it can be through the sample, or it can be around the sample also. The light going around the sample, and it is not being deviated, it is the same. So it is called the undeviated light. Then there is some light which is going from the source to the sample, and it is interacting with it in some way, and because of which it is out of phase by 180 degrees, or it is out of phase, and that light is called as a diffracted light. So this light, when it falls on the objective, it is out of phase as out of phase to the undeviated light. Now this the image that we see is nothing but the interplay of both of these diffracted and the undeviated light. So there is a destructive interference between the undeviated and diffracted light, which gives rise to the different intensities of light. So there are some dark regions and some bright regions. So bright regions are because of these undeviated light, and the dark regions are being created by this destructive interference between these two forms of light. So what we see as an image is nothing but these bright and dark images, these bright and dark regions only. Bright regions are because of the undeviated light, and the dark regions are being formed because of the interplay of these two lights. So in the image here, you can see that in the A subfigure, you have this at the center, the undeviated light. So the undeviated light which is falling directly to the objective, and this is the image that we see, a very bright central spot. Now as we move away from the center, there are the higher orders. The central one is called the zeroth order diffraction, and as we move away from the center, there are the first orders and the second order diffracted regions that are observed. And as you can see, the blue and red regions are separated. So the blue light interferes and appears as blue, and the red light interferes and appears as red. So this diffraction orders are seen. So in the B subfigure, you can see a fan-like shape is being created, undeviated light being concentrated in the center, and the diffracted light appearing all around it like a fan. So to capture the minute details, we want more diffraction orders to be gathered, more of these diffracted light to come to the objective. That is the purpose that we desire. All the diffracted light should come to the objective to identify the minute details. So this this brings us to the topic of resolution. So resolution is what we aim for, a greater resolution. What is resolution? Resolution is the minimum distance between two separated points. So we have two separate points, and the distance between them is what defines the resolution. We want highly resolved images. So in terms of digital images, resolution is measured by the number of pixels per unit inches. So the more the pixels, more the resolution. As you can see in image D, in image D, in image D, only a few pixels are there. So very few pixels are present. Only 7-8 pixels are there, which are not able to, like, we are not able to make out what the image is. We are unable to see the image. But as we increase the number of pixels, as we make the array more denser, as you can see in C, there is a variation of bright and dark regions, but still the image is not clear. As we move to B, in B we can see that by making more pixels, we are getting some sense of the image, but still it is not very clear. And as we move to A, we can certainly see that this is a map of some area. So it is a top view of some area, and it is a very it is a highly resolved image. So in the era of smartphones, Androids, like, the picture quality matters a lot, and we need more and more resolution of images. So that is the purpose of designing these sophisticated devices, to get resolved images. So how can we tune the resolution of our microscope? So the Rayleigh equation gives us the relation between so the Rayleigh equation helps us in this. So it is D is equals to 1.22 times lambda divided by Na. So what is D? D is the space between two adjacent particles, and it is indicative of the resolution. Smaller the value of D, the greater will be the resolution. Lambda is the wavelength of light used, the source, and the Na is the numerical aperture of objective. Na is the numerical aperture of objective. So what is numerical aperture? Um it is it basically tells you how much light can be gathered through the objective, what is the angle at which it can accept the light. So as you can see from this formula, we want a smaller value of D for greater resolution. Smaller value of D means we need a smaller lambda value and a higher numerical aperture value. So a combination of these three is able to produce a high resolution image. So we need a high numerical aperture, apochromatic lenses, and small wavelength, usually a blue light source. So these three can give you a good resolved images, but these are not alone. There are many other factors that can influence the resolution, but yes, these three are um, the main ones. So apochromatic lenses, what are apochromatic lenses? These are aberrations corrected lenses. It has an array of lenses in the objective, and it is very much expensive, and basically the chromatic aberrations are corrected in these type of lenses. So in the bottom left you can see a image that is, so the resolution can be enhanced using if you use an oil immersion between the objective and the sample. So when you use a dry objective, a dry objective, this fan, the amount of diffracted light reduces. But when you use an oil immersion, which is having a higher refractive index, more of diffracted light enters into the objective, and which is able to produce a greater resolution in the image. So as you can see the diffraction in the A, as you can see the diffraction pattern in A, it is not very much resolved as compared to B. B is highly resolved, and that is because of the greater diffraction orders the lens can capture. So in these way, the resolution of your the resolution of the microscope can be tuned. Now, to capture the minute details of the object, after the intermediate plane, our rays enter into the eyepiece. So at the eyepiece, this airy disk formation takes place. So at the eyepiece, after the image goes through the rear focal plane of the objective, it goes to the eyepiece, and there these airy disk formation happens. A large numerical objective, a large numerical aperture gives a smaller airy disk, whereas a smaller numerical aperture gives a large radius of this airy disk. And beneath it, you can see the intensity of light, the relative intensity of light. So the undeviated light is the most intense, of course, but the diffracted orders you can see are also, they are intense. And as we increase the numerical aperture, the size of this airy disk reduces, and but the intensity is very much high. The intensity, you can see the relative intensity is significant. Now, when you want to resolve two images, their centers should not overlap. If the centers are overlapping, you will not be able to. If the centers of the airy disk are overlapping, you cannot resolve the image. So this E figure shows you the limit of resolution. It is just, it is the circles, the centers of the airy disk are separated in such a way that just you have reached the limit of resolution. If if they were a bit closer than this, then you would not have you will not be able to resolve. But increasing the separation further, you can see the particles distinctive. You can very easily see the separated particles. So coming to the objective specifications. Now, the objective can have many like objective are designed for for um, specific purposes, and they are there are many specifications that describe a objective. Starting from the screw thread, you have the coming on these labelings. So the first is the manufacturer. Okay, this is fine, but then you have a 60x. So this is the linear magnification that can be achieved. 1.40 denotes the numerical aperture, and oil is for the immersion medium that can be used with this objective. Then you have infinity. Infinity means it is an infinity corrected microscope. It is compatible with an infinity corrected microscope. The cover slip thickness is 0.17. The working distance is 0.21. The color code, the finger grip, all these comes under the specifications of an objective. And it is important to choose wisely which objective to use for a given object. So, using optical or light microscopy, we can see images which are resolved up to 200 nanometers or zero point 0.2 micrometers. So, up to zero point 0.2 micrometers distance, we can use light microscopy. So that means we can see crystals clearly under a light microscope. The morphology can be seen, but if we want to gather atomistic details, it is not possible through a light microscope. Then you need to go to more advanced techniques, that are the electron microscopes. So in the realm of optical microscopy, we have come a long way. Like the first of the lenses and the setup was done by Abbey and one other person in 1886. So in the late 18th century, the field of microscopy started, and now we are here with many advances in microscopy, such as we have polarized light microscopy, dark field microscopy, phase contrast, differential interference, and many more. And the field is emerging just to produce more resolved images, more 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 um, more better like better images. And because of this, all these sophisticated facilities are being created. So looking forward to much more better images. I think we have reached a lot more. And so this was all about microscopy, and I hope you must have understood the fundamentals of image formation, how our image is getting formed, the basic, the 11th, 12th grade, the ray paths, how the light travels, how it interacts, and how it forms an image eventually. So, this is a beautiful and a basic principle that drives the field of microscopy, and it is very much relevant in all these sophisticated forms of microscopy, also. Yes. Thank you.